Welcome back. In the last video, we proved an important characterization of finite extensions to be Galois. So let me just recall the statement here. So we showed that a finite extension is Galois if and only if it is the splitting field of a separable polynomial over the base field f. Okay, so today we are going to start discussing towards the main theorem of Galois theory, but I thought this is a good time to quickly recap some important things that we have learned in the course. So sort of a revision or recap. So I am going to write this down so that it is clear to you, and I have done them over the last few videos. Okay, so I am going to recall a few things. So let K be a field. This is something that I have written in the past. So and S is any set of automorphisms of K, and G is a group of automorphisms of K. Okay, so S denotes the set, G denotes the group. So some of the things that we have done, so these are all done. You can go back and look at the appropriate videos here. So the degree of the field extension K over Ks is at least the cardinality of S. But if you take the group, you get exactly the cardinality of the group, the order of the group. Okay, and we also showed that Galois group of K over K G is precisely G, and these are general facts that always hold. So there is no further assumption about the field K. The last statement that I want to recall in this situation is definition of Galois extensions. So K over F is Galois. So I am going to write further things here today, but let me recall the definition. If F is K power Galois K over F. Right. So this is the definition of Galois extensions. An extension is Galois if this happens. So in general, we know that the fixed field is an intermediate field between K and F. It certainly contains F because these are all F automorphisms of K. Okay. So, but if it is equal to F, we say that it is a Galois extension. Okay. So some other things. So these are so far this was done earlier, and I recalled these as it is. But now I am going to recall some other facts. Okay, or observations. These are not explicitly mentioned before, but I want to list them here because this is a good way to list the important things that we are going to require later on. So let K over F be a finite extension. Then the order of the Galois group divides the degree of the field extension. So in particular, the order of the Galois group is less than or equal to the degree of the field extension, and this is a triviality because you have K power Galois K over F and over F, right? So this is always an extension, and this degree is exactly the order of Galois K over F, right? So this is equal to this, the degree is equal to this. So because of the multiplicative property of the field extensions, this divides the degree of K over F, because degree of K over F is K colon K power Galois K over F times K power Galois K over F colon F. So this is a triviality. Okay. So the sixth statement that I want to write is that every finite separable field extension K over F can be extended to a Galois extension. So I am calling this a recap, but technically it is really not a recap, but I just want to explain why this is the case. So let us say K over F is a given Galois extension. So K can be written as alpha 1, alpha 2, given separable extension. It is a finite separable extension, so expressed like this. So we can always choose like this, and let us say Fi is the the irreducible polynomial of alpha I over F. So each Fi is separable by hypothesis, right? Because K over F is a separable extension. Each Fi is separable. This implies F, which is defined to be F1 to Fn, is also separable, because irreducible factorization of F is this F1, F2, Fn, and each of them is separable, so F is separable. Now let L be the splitting field of F over K, let's say. Okay, so what you have is, so now L sits above K and you have the given extension here. So I claim that L is Galois over F. So this is what I mean by this. So you can always extend the given extension to make this Galois. Okay, this is because L over K is, so this is the verification of this I will leave for you. You can do this in any number of ways, but the point is L is the splitting field of K over F over F also, splitting field of F over F also, because F is a polynomial in capital Fx, it is a separable polynomial and it is generated by the roots. So L is Galois over F, or you can argue that it is normal and separable separately. So this is a useful property for us. Every finite separable extension, given finite separable extension, can be embedded in a Galois extension of the base field. And I'll remark here that this is not true if K over F is not separable, right? Because if K over F is not separable, you put any field here, this cannot be separable, because we argued already in the videos when we discussed separable extensions that if L over F is separable, L over K and K over F are separable. So if L over F is separable, K over F will be separable, but K over F is given to be not separable. So L over F cannot be separable, and hence if L over F is not separable, implies L over F is not Galois, because a Galois extension is separable. So if it's not a separable extension, it cannot be Galois. So if you are given a non-separable extension, you cannot extend it and make it a Galois extension. Okay, and finally let me summarize all the equivalent conditions for a Galois extension. So let K over F be a finite extension. The following are equivalent. Okay, TFAE always stands for the following are equivalent. The first statement I want to make is K over F is Galois. This is the first statement. Second statement is F is K power Galois K over F. Of course 1 and 2 is just the definition, but I wanted to nevertheless write this because it's a good way to keep track of all the equivalent conditions for being Galois. So 3 is something we have discussed also. K colon F is the order of the Galois group, right? So this is same as being Galois. Fourth, K over F is normal and separable. Again we have shown that this is same as being Galois. And finally 5, K is the splitting field of a separable polynomial over F. So K is the splitting field of a separable polynomial over the base field. Okay, so this is just a convenient way of remembering all the equivalent conditions for a Galois extensions. So this is something that I wanted to write so that you have this slide in front of you and you can often refer to this. So these 2 slides so far are the 7 facts that I wanted to record. Many of them are recaps or essentially trivial extensions of what we have learned. Only 6 really is new for you, or 5 and 6 are explicitly mentioned for the first time, but these are 7 facts that I wanted to highlight for you before we proceed. Okay, so the next goal is, as I said, next goal is to prove the main theorem of Galois theory, also called the fundamental theorem sometimes. Okay, so before we state and prove it, it's a fairly simple proof actually, however it's an important starting point for the study of Galois theory. So main theorem I should call, not theory, it's a specific theorem. So we'll first motivate using some examples. So I'm going to give you 2 examples to describe the 2 or 3 examples to give you a flavor of what main theorem does. So the first example is something that we have discussed in detail before, but I want to quickly discuss this. K over F is Galois. So we already know K over F is Galois. Okay, so let's analyze this. What is a Galois group? We also know that, and the Galois group K over F is I have denoted this by this. This of course we know also for abstractly, this is the Klein 4 group, which is equivalent to, which is isomorphic to Z mod 2 cross Z mod 2. And I wanted to, Galois main theorem connects the intermediate fields of the given Galois extensions in the subgroups of the Galois group. So what are the subgroups? So here, so let's call this G for convenience. So I want to do this in this slide, so the entire picture is in front of you. What are subgroups of this? So let's start with this. What are subgroups of Okay, so G is a group of order 4. It has 5 subgroups really, right? So there are 5. There are 5 subgroups. What are they? Of course, we have 1 and G, the trivial group and the full group. And then we have also 1 comma sigma 1, 1 comma sigma 2 and 1 comma sigma 3. So we have H1, H2, H3. Okay, so the tree of field, the subgroups will be like something like this. So I have G and 1 here, and all the other 3 are basically, so maybe I will write this down after some time. So these are the 5 subgroups. You have trivial group, full group, H1, H2, H3. I want to find out what are the fixed fields of these groups. So find the fixed fields. So let's find the of these 5 subgroups. So I have already alluded to this in the previous video. If you have a group containing another, there will be an opposite inclusion for fixed fields. So what is a fixed field of 1? So these are things that are fixed by 1. So that is exactly K. What is a fixed field of G? Because it is a Galois extension, this is F, right? That is Q. On the other hand, what is the fixed field of H1? So now I am going to recall for you what sigma 1 does. So maybe I will write it here. Sigma 1, it does not really matter what whether you change these, but I wanted to be precise. So sigma sends 1 sends I to I, minus root 2 to minus root 2. Sigma 2 sends I to minus I, root 2 to root 2. Sigma 3 sends I to minus I and root 2 to minus root 2. Okay. So the first 2 things are not interesting. The fixed field of the trivial group is K, fixed field of the full group is F. But what is the fixed field of H1? If you think about it, I is fixed here, right? So I is fixed, so that means it must be Qi. Okay, this is something that we have discussed at length in the past, because it's a degree 2 extension, it contains I, so it must be I. Similarly, fixed field of H2 must be Q root 2 and fixed field of H3 must be I root 2. Okay, and now I'm going to draw the tree of groups on one side, fields on the other side. So you have G and 1, and you have H1, H2, H3. Let's denote this. Okay, so this bar here represents the fact that the bottom one contains the above one. This is the opposite of, this is the reverse of the field situation. What is the fixed field of G? We agreed that the fixed field of G is Q and the fixed field of 1 is K. And then you have the Q root 2 or Qi, so just to be Q root 2, Qi root 2, right? So, and we have these inclusions. Here a bar represents the top one contains the bottom one. At the group level, the bar represents the bottom one contains the top one. So G contains Hi and Hi are in 1. Okay, so that is the convention. So now the question that I want to ask is, the subgroup tree is completely written down because there are no other subgroups. It is just a group of order 4 and it's very clear that these are all the subgroups, there cannot be any other subgroup. But what about the intermediate field tree? It is conceivable that there are other intermediate fields. Okay, so now this is what I want to address when we do main theorem. The claim that we want to make is the tree below shows all the intermediate fields of the extension. Okay, so that means there are exactly 5 intermediate fields of K or F, K and F themselves, and these 3 proper intermediate fields. And the reason for that, and we will formally prove this in the main theorem, is that every time you take a intermediate field, maybe there is a mysterious field outside these, you can take the Galois group of that and that will give you a subgroup. Okay, so the first statement of the main theorem is there is a bijection between subgroups of the Galois group and the intermediate fields of the extension. Okay, so this I don't want to do this in detail because we will prove this anyway, but the point is there are no other intermediate fields. And orally I will simply say again that if there is an intermediate field, you can take it the Galois group of K over that intermediate field and that must fit into this. So it must be one of these, but then if it is one of these, that intermediate field must also be one of these. Okay, so this is the reason for the fact that these are all the intermediate fields. Okay, and now I will also emphasize another fact here. K over F is Galois is given. So this implies K over, let's call this F1, not F1, L1, L2, L3. So K over L1, K over L2, K over L3 are all Galois. Right? This is just a feature of Galois extensions. You have a Galois extension, the top one is Galois over any intermediate field. So these are Galois. Okay, so let me not write those, but let me write the degrees here. So this is degree 2, this is degree 2, this is degree 2, this is degree 2, this is degree 2. And here I am going to write the index of this. What is the index of this? This is 2, this is 2, this is 2. Okay, every number here is 2. We will see in a minute why these are important. But what about L1 over F? In fact, L1 over F, L2 over F and L3 over F are also Galois. These are not in general true, right? We know that this bottom part is not in general true, but in this case they are also Galois. Okay, so this is the first example. Let me let me do one more example to illustrate again some features of this. So here I am going to take q adjoint cube root of 2 comma omega over q. Okay, so this is a degree 6 extension and this is a Galois extension because this is the splitting field of x cubed minus 2 over q, right. So here, and we also know that the Galois group G is isomorphic to S3. I have, without maybe proving this carefully, I did say this at some point, and now I'll just give you exactly what the generators are. Okay, so here define sigma from k to k. Remember, k is generated over q by cube root of 2 and omega. So to determine an automorphism of k, all you need to do is tell where the image of cube root of 2 and what the image of omega is. Cube root of 2 can go to either cube root of 2, cube root of 2 omega, or cube root of 2 omega square. Omega has to go to either omega or omega square. So let's say cube root of 2 to omega cube root of 2 and omega to omega. Okay, and let's define tau to be cube root of 2 goes to cube root of 2 and omega goes to omega square. Okay, so then I will let this leave this as an exercise for you. I will maybe say a few things and then I'll move on. G is exactly equal to 1 sigma sigma square tau sigma square tau. Okay, and it is isomorphic to S3. So the relation is the following. So tau sigma is sigma square tau. Okay, so you verify these are just direct calculations. For example, what would be sigma square? Sigma square sends, you can see, cube root of 2, first will go to cube root of 2 times omega, then you send omega to omega, cube root of 2 to omega cube root of 2, so that's omega square cube root of 2, omega will go to omega. Okay, so this is a new element, right, whereas sigma cubed will send cube root of 2, so now you apply sigma again to this, omega square will go to omega square, but cube root of 2 will go to omega cube root of square. So this is omega cubed cube root of 2, which is cube root of 2, omega will be omega. So this is equal to 1. So sigma is an order 3 element. Tau square, of course, is identity because cube root of 2 is anyway fixed. Omega goes to omega square will go to omega square square, which is omega 4, which is identity, and so on. So I won't maybe check the other things, but this is left to you. So in fact, what you can show is that order of sigma is 3, order of tau is 2, in fact order of sigma square is also 2, 3, and order of sigma tau equals order of sigma square tau. These are degree 3 elements. So there are 3, so there is 3 degree 2 elements and 2 degree 3 elements and 1 degree 1 element, namely the identity. So this is the nature of the group G. So this is the well-known group to us, symmetric group. So now for each of these subgroups, I am going to write the tree of, and then on the fly I will write down the fixed fields. So we have G, and of course we have. So let me give some names to these. Okay, so it will be easier. So I will call H prime to be the order 3 subgroup, and H1 to be 1 comma tau. There will be 3 order 2 subgroups corresponding to 3 degree 2 elements. So H2 will be 1 sigma tau and H3 will be 1 sigma square tau. So apart from the trivial group and the full group, these are the 4 proper subgroups. So these are 6 subgroups are going to be there. So G, and I am going to write index 3 thing here. So this is index 2 thing here. H prime is index 2 and index 2 things will be here, index 3 things will be here, and they are all of course going to contain the trivial group. and here index is 3 because this is order 3 and this index is 2. Now what are the, so this is the tree of subgroups. And what are the tree, what is the tree of subfields? Intermediate fields. So of course we have Q and we have K. So those are the corresponding fixed fields. G has fixed field Q because it's a Galois extension. 1 has fixed field K. Now what is the fixed field of H prime? It must be, because H prime is an order 3 group, it must be in a field such that degree of K over that is degree 3. So if you look at sigma, what is fixed under sigma? Sigma is going to fix omega. Similarly, sigma square will also fix omega. So if you take Q omega, right? So if you take Q omega, this is going to be a degree 2 extension of Q and it will be a degree 3 extension of. So Q omega is contained in K power H prime, and K power H prime is a degree 2 extension of Q. So it must, Q omega is also a degree 2 extension of Q. So this must be that. So this is KH prime. What is KH1? What does tau fix? Tau fixes cube root of 2. So cube root of 2 is here. That's a degree 2 extension and this is a degree 3 extension. So this is equal to K power H1. Now what is K power H2? What is sigma tau? So I'm going to write down sigma tau because it will be useful to write down the fixed field. So just write down what is sigma tau. Sigma tau, where does it send omega cube root of 2 to? First you see where tau sends cube root of 2 to. Tau sends cube root of 2 to cube root of 2 and sigma sends cube root of 2 to omega cube root of 2. And where does omega go under this? So omega goes under tau to omega square, under sigma it will go to omega square. Now it doesn't look like it fixes anything, right? But where does omega cube root of 2 go? Omega cube root of 2 will go to omega will go to omega square and cube root of 2 will go to omega cube root of 2. Okay, so that's omega, that is cube root of 2. Even that's not fixed. What about omega square cube root of 2? Where does that go? So that goes on to omega square will go to omega square whole square, that's omega, and cube root of 2 will go to omega cube root of 2. So this is omega square cube root of 2. So that is a fixed element of H2. Okay, but now you can argue that that will have degree 2 over Q. So I'll write it here, Q adjoined omega square cube root of 2. So that's a degree 2 element, degree 2 extension, that's a degree 3 extension, sorry, this is a degree 3 extension, this is degree 2, and I claim that this is K power H2. So you can check that because it is fixed, omega square cube root of 2 is fixed by H2 and that's supposed to be a degree 3 extension of Q. So there is a lot of stuff going on here, we are using everything that we have done so far. So finally you have Q adjoined omega cube root of 2. And this is going to be K power H3. Okay, this is degree 2 and this is degree 3. Okay, so these are dual pictures. You have tree of fields, tree of intermediate fields. And again, as before, there are no other intermediate fields. This is going to be a consequence of the main theorem. Okay, now let's notice which of these are Galois. So of course this is Galois, so I'll write G for that. This is Galois, this is Galois, this is Galois, because K over Q is Galois, right? K over Q is Galois, so K over all these intermediate fields is Galois. But the bottom ones in general are not Galois. In this case they happen to be Galois. This is Galois. But what about these? This being a degree 2 extension is Galois, but this is not Galois. Okay, that we have seen because the conjugates are not there. Similarly, this is not Galois and this is not Galois. Okay, so I want to now emphasize which property of the group side determines that. So I claim that this is a normal subgroup, but this is not normal. This is not normal, and this is not normal. H1, H2, H3 are not normal in G. Okay, so that is equivalent to the fact that KH1 KH2, KH3 are not Galois extensions of Q. Okay, so this is just an observation I am making, but we will prove this in the main theorem. So here, of course, the Galois group is abelian. So everything is normal, right? So these are normal, normal, normal. So these are normal, hence these are Galois. So here this is normal, so this is Galois. These are not normal, so this is not Galois. Okay. So whether the bottom half of the Galois extension is Galois or not is determined by whether the corresponding subgroups are normal or not. Okay, let me quickly, I want to end this video soon, but I want to give you one more example, but this I will not do in detail. Let's take this. So P is a prime number as always, R is a positive integer. So this of course is Galois, and Galois group is a cyclic group of order R. Okay, so I want to, without drawing the tree, I want to just allude to this. Subgroups of G, so let's call this G are cyclic groups of orders dividing R. So basically what I am saying is that for every S that divides R, positive integer, there exists a subgroup of G of order R. So let me just let's call that H. So I want to just highlight what the corresponding picture is going to be. So G has order R. So H is order R, that means H has index 1 has index this in R, and this, okay, so this is not R, this is S, and this is R by S, right, because index will be R by S. And now at the field level, the fixed field of G is F, of course, because it's a Galois extension. Fixed field of 1 is of course the full field. What is the intermediate field corresponding to this? This extension is going to be of degree equal to the cardinality of H, right? So that is exactly S, and this is R by S. Okay, but what is this field here? So K power H is a field which has index R by S. So that means the cardinality of K power H is R by S, P power R by S. But such a field exists, right? We know that such a field exists, and this is a subfield of, we know already from the structure theorem of finite fields that a field of order, let us say K, which is R by S, exists, P power K, where K is R by S, exists. So that of course we know, but we also know from the structure theory. So K power H I am claiming is F P power K. K is again R by S. And not only that, moreover, f p power k is contained in f p power r because k divides r. So that is a subfield. Okay. Now all subfields here will be of the any subfield of k must be of the form f p power n where n divides r, right. So this is one of the exact statements in the structure theorem of finite fields. So this exists, let us say this is f p power n. Now this corresponds to a subgroup of G. Okay, so this I went over very fast, but the idea is that because G is a cyclic group of order R, there is a subgroup of every divisor of R. Similarly, there is a subgroup of every index, any possible index. So there will be a subgroup of index n, whose fixed field will be the field f sub p power n. Okay. So I wanted to introduce another class of fields to illustrate main theorem. So I did not spend too much time on this. Maybe I'll come back to this later and talk about this. But these three examples are supposed to give you an idea of how the group theory of the Galois group, namely what are the subgroups, what are the normal subgroups, is supposed to shed light on what are the intermediate fields of the given extension and which are Galois. Okay, so just let me end this video with the final comment, which is that everything here is Galois. All intermediate fields are Galois extensions over F, because any extension of finite fields is Galois, which corresponds to the fact that G is abelian and every subgroup is normal. Okay, so this is akin to the first example where everything is normal, and this is different from the second example where there are non-normal subgroups corresponding to non-Galois extensions. Okay, so let me stop this video here, and now we are ready to state and prove the main theorem of Galois theory, which we will do in the next video. Thank you.